Welcome all to our first Ray Summit. When we started Ray and later when we started Anyscale, we are driven by the belief that the future of computing is distributed. Now, distributed computing is not new. Almost every decade, a new category of application was distributed. Arguably, the first distributed system was the ARPANET, the precursor of today's internet, which started in the early 1970s. ARPANET gave researchers the ability to remotely access the few powerful mainframes across the country. ARPANET also led to the creation of email by Ray Tomlinson in 1971. 1980s saw the emergence of high-performance computing, or HPC for short. HPC started in 1985 with a partnership between National Science Foundation and 5 other universities. This led to powerful simulators which allowed engineers and researchers to design airplanes, do weather prediction, molecular modeling, and much more. 1990s saw the rise of the internet and of the web. This led to building highly distributed systems to support popular websites visited by hundreds of millions of people. In 2000, we saw the emergence of big data. As the internet companies are accumulating huge amounts of data, they wanted to get a better understanding of their users to improve their users' experience as well as their own businesses. So, as you can see, over the years, more and more workloads became distributed, and once they became distributed, they remain distributed. Despite all these developments, distributed computing is still an exception. Today, distributed computing is very hard. It requires you to be an expert, and thus it remains inaccessible to most developers. To compound to this challenge, few universities offer distributed computing classes to train such experts today. But we believe this will soon change. Driven by the demand, we believe distributed computing will become the norm rather than the exception. So what is different this time around? Well, 3 things. The rise of deep learning, the end of the Moore's law, and more applications becoming AI-centric. I'm going to discuss each of these trends next. First, deep learning demands are growing faster than ever. This is a famous OpenAI plot showing that over the past 8 years, the computation required to train the state-of-the-art models has astonishingly increased 35 times every 18 months. And this is not only true for esoteric models like learning how to play games such as Go or Dota 2, but also for models targeting practical applications like language translation and image processing. And it's not only true for processing, but for the memory as well. Here is a plot of the model sizes for the past 4 years. It shows that the size of the state-of-the-art models has increased 20 times every 18 months. And if you look at the past 2 years alone, it has increased 200 times every 18 months. This is just unheard of. On the other hand, the Moore's law has ended. Indeed, as shown here in another famous plot, the performance of a single processor core used to double every 18 months. Now, it increases by just a few % over the same time period. To put things into perspective, here we show the performance increase of a single core overlaid over the OpenAI plot. As you can see, the performance gap is just huge. In fact, even if Moore's law hadn't ended, it will still fall way short of satisfying the demands of training these models. So what about specialized hardware, you may ask? After all, we are living in the golden age of the specialized processors that trade generality for performance, such as GPUs and TPUs. Well, it turns out that even those are far from enough to fill the performance gap. Here we are overlaying the performance of NVIDIA GPUs and Google TPUs over the same OpenAI plot. As you can see, while they do provide orders of magnitude improvements over a single processor, their performance doesn't grow faster than the Moore's law. So they still fall way short of the demands of the machine learning models. And this is true for memory as well. Over the past 4 years, the GPU memory has increased about 1.5 times every 18 months, while the model size, again, has increased 20 times over the same time period. And unlike processing, we cannot do much about memory in the way of specialization, as we still need a couple of transistors to store a single bit of information. Thus, to support these machine learning workloads, there is no other way than distributing these workloads. Finally, most applications are becoming AI-centric. Indeed, virtually every application is incorporating now elements of AI, including e-commerce, financial applications, manufacturing, healthcare, and many more. Furthermore, more and more of these applications are starting to integrate AI with other distributed workloads. This has not been the case so far. Traditionally, distributed workloads have been isolated. Indeed, HPC, big data, and microservice applications have been using different software stacks and run on different types of clusters. However, this is changing. Not only applications are becoming AI-centric, but more and more of these applications integrate AI with other distributed workloads. AI is already overlapping with high-performance computing. Distributed training systems like Horovod are leveraging MPI, a system developed by the HPC community over the past 30 years. Similarly, some industrial reinforcement learning applications are leveraging large-scale simulations running on HPC clusters. AI and big data are strongly overlapping, as most AI applications today need huge amount of data to train sophisticated models. Finally, the microservice architectures that power many of today's backend services are starting to integrate machine learning components to improve these services. In summary, on one hand, the demands of the AI application are growing much faster than the capabilities of a single processor or a single machine. On the other hand, virtually any application is becoming AI-centric, and these applications are more and more integrating AI with other distributed workloads. We believe that these trends together will soon make the distributed applications the norm rather than the exception. Unfortunately, developing distributed applications today is extremely hard. Despite the convergence of distributed workloads, systems used to support these different workloads are as diverse and distinct as ever. There is no single framework to support end-to-end distributed application integrating these workloads today. So what do people do when they have to develop such applications? Well, they have three solutions. And here are how these solutions compare along two axes: generality and ease of development. The first and the most common solution is to stitch together existing frameworks. For example, Spark for data processing and insights, Horovod for distributed training, Seldom for serving, and Spring for business logic. The challenge with this solution is that each of these frameworks has a different API, which makes development hard. Similarly, deploying and managing multiple frameworks can be very challenging. Second, you can build the application from scratch, for example, using Kubernetes, Docker, gRPC, and maybe Golang. While this approach is the most general as it enables you to build virtually anything, it can be very costly in terms of cost engineering and time to market. As a result, very few companies can afford to take this approach. Finally, people are increasingly considering serverless. Since serverless abstracts away servers and clusters, this is by far the most developer-friendly solution. Unfortunately, it comes with a slew of limitations and constraints. First, most popular serverless solutions are cloud-specific. Second, they do not support stateful computations, which makes them a poor fit for applications such as model training and microservices. Finally, the current offerings do not support GPUs and TPUs, and they limit the computation time of a function, for example, to 15 minutes. With Anyscale and Ray, our promise is to provide a platform for building end-to-end applications, a platform that is both general and easy to use. Thus, our mission is simply to make distributed computing easy. So what do we need to accomplish this goal? Well, if you ask a developer what is her preferred development environment, she'll likely tell you, my laptop. Developers love their laptops. Unfortunately, a laptop doesn't have a few things that developers also want, like lots of resources, different type of resources, like GPUs and TPUs, and availability. For example, you cannot run a service on your laptop. So developers also want the power of the cloud. In other words, what developers really want is an infinite laptop. They want to have the same development experience as on their laptop, but they want their laptop to have access to lots of resources, different kind of resources, and be always on. And this is what we are trying to build for you at Anyscale. This is our vision. So how do we do this? In a nutshell, we are building a service to provide the illusion of an infinite laptop and use Ray to program it. By using Ray, you also have access to a rapidly expanding open ecosystem of scalable libraries, as Robert described in his keynote. The Anyscale service has three desirable properties. First, it provides laptop experience with the power of the cloud. Second, it provides serverless experience while obviating its limitations. And finally, it is multi-cloud native. To provide the laptop experience with the power of the cloud, Anyscale automatically syncs your code from your laptop to the cloud. This allows you to edit the program on your laptop using your favorite editor and execute the code in the cluster without any context switching. Furthermore, Anyscale has built-in dashboard that provides detailed resource utilizations and debugging information at your fingertips, like you have on your laptop. Second, Anyscale provides serverless experience without serverless limitations. By serverless experience, we mean that it abstracts away servers and clusters, so you do not need to worry about those when you are writing or running your application. Under the hood, Anyscale will allocate the right resource instances, and it will auto-scale to match your application demands. Furthermore, Anyscale removes many of the limitations of today's serverless solutions. First, Ray is open source and thus cloud agnostic. Second, it supports stateful applications like serving and training. Lastly, It provides GPU and TPU support and has no runtime limitations. Finally, Anyscale is cloud native. What we mean by this is that it enables you to select a cloud when starting an application and use multiple clouds at the same time. For example, you can train your model on GPUs and TPUs in one cloud and serve on CPUs in another cloud to save cost and shorten the product development lifecycle. In summary, our premise is that the future of computing is distributed and that the distributed application will become the norm rather than the exception. Unfortunately, today, building distributed application is extremely hard. Our mission is to make this easy by providing you with the best development tools for building distributed applications. And we do so by building a service that aims to provide you with the illusion of an infinite laptop that you can program with Ray. While we are just starting to make this vision a reality, we are today very excited to share with you our first steps. So please join me to welcome Edward Oakes, a software engineer at Anyscale and a former Berkeley graduate student who will demo the Anyscale product. Thank you.